Grade 12s, welcome to the video Optimization Part 2. And as promised in the video on Part 1, I am doing the Luzandi method going step by step by step. Right, so this question, very important, how to solve a maximum and minimum word problem. So you'll remember in the previous examples that we did, we just kind of followed the idea. But hopefully, if you recall the previous examples we did, then these steps won't actually seem too strange to you guys. So in order to solve a maximum or minimum word problem, in other words, optimization, step 1, you need to identify what is being optimized and set up an equation. They might ask you for a maximum area, so you need to set up an equation for area. Or they might ask you for a maximum volume, then you need to set up an equation for volume. So that's the first step. Identify what it is that's being optimized and set up an equation. By the way, remember, it's not always going to be a maximum. It could also be a minimum. Like, for instance, a minimum area might actually minimize cost. So sometimes a minimum is a good thing. So minimum, maximum, it really doesn't matter. Identify what is being optimized and set up an equation for that. I'm then going to refer to this equation as the optimization equation in the rest of the steps. So step 2 then says, use the additional information to set up a second equation. Now there's going to be information given that doesn't have anything necessarily to do with what is being optimized. So they will talk here about you optimizing area, but then they'll give information here about the perimeter of the shape. Or they'll talk here about optimizing volume, and then over here they might give you information again on the perimeter or even on the area of the shape. So that second piece of information is specifically to set up a second equation. Now, why are you setting up that second equation? That second equation is here for step 3. We need to substitute that second equation into that optimization equation. Why? So that the optimization equation only has one independent variable. I did show you that in the examples in the previous video, where the moment we have two variables, it doesn't work. I have to have one independent variable in order to find the derivative. Then, once I've substituted in, I now have an optimization equation with one independent variable, which then allows me to continue to step 4, differentiate the optimization equation and set it equal to 0. That, people, right there, set it equal to 0. You shouldn't even think about it, because whenever I'm trying to get a maximum or a minimum, it's always the derivative equal to 0. Now that gives me an equation. So step 5, you solve that equation, the derivative equal to 0, and if necessary, this is only if necessary, you then need to sub the answer back into that original optimization equation. Why? It depends on the question. If the question just says, for which dimensions do I have a maximum volume, you can stop there. You don't need to do the sub back. Okay, so you just solve the equation. But if they don't ask for which dimensions do I have a maximum volume, if they actually ask you for the maximum volume, then whatever value you get there, you will need to sub it back in order to get that maximum volume. So we're going to do some past paper problems using these steps, and hopefully then you'll see how these steps work. The first problem was from last year, the 2019 IEB paper 1. So 2019 IEB paper 1, and it was question 10. It says, an oil tank structure, as shown in the diagram below, consists of a cylindrical body, so you've got a cylinder over here, of length h meters, so they've got h meters over there, and 2 hemispherical ends of radius r, so they've got a radius there for those hemispherical ends of radius r, and has a volume of 1,000 meters cubed. Now careful though, that 1,000 meters cubed is the entire shape, so it's the cylinder plus those 2 hemispheres. And obviously, people, 2 hemisphere make a full sphere. So I really don't need to add 2 hemispheres. I can just go and say 1 sphere makes up the 2 hemispheres. Then they ask, determine the value of r such that the total surface area of the tank is a minimum. So I'm just going to highlight that, because remember, step 1 says we need to identify what it is that I need to optimize. In other words, minimum or maximum. And in this case, they said the surface area. So that's going to come into my step 1, where once I've identified what needs to be optimized, in this case minimized, I need to set up an equation for surface area. Okay, and it says show all your working justification, and it gives you a bunch of formulas: surface area of a sphere, surface area of a cylinder, volume of a sphere, volume of a cylinder. So we'll get back to that just now. So step 1, identify what's being optimized, surface area, and set up an equation for that surface area. So the surface area we've got over there, surface area of a sphere is 4 pi radius squared. And like I explained to you guys, the two hemispheres make up a full sphere, so that's 4 pi radius squared. But I also have that cylinder over there. Now careful though, because this particular formula gives me that curved part, the round part, gives that to me. This one closes up the front and the back. But I don't need to close up the front and the back. I just need to get the curved part because the hemisphere actually closes it up. So that's why I'm just going to go, this is not necessary. I'm just going to use that 2 pi radius times h. Now you'll notice this is now the optimization equation, but I have a problem here. Instead of having only one variable, the variable r, which is what I want, because it did ask for the value of r, I also now have h over here. So this is why I need to now look at the extra information and I need to set up a second equation. That second equation will have to have something again with r and h so I can substitute in. So the additional information that they've given me here is they told me it has a volume of 1,000 meters cubed. So now talking about volume, which is not what I'm trying to optimize, but that is a second equation I can use. So I can say the volume of this particular shape is then going to be the volume of the sphere. So 4 over 3 pi radius cubed, there we go, plus the volume of the cylinder, which is pi radius squared times height. And they've given me the fact that the volume is equal to 1,000, so I can substitute that volume with 1,000. Right. Now, this particular equation, again, this is not what I'm trying to optimize. I know that the volume is 1,000. I'm not trying to maximize or minimize the volume. But I'm writing this down specifically so I can do a substitution. And that substitution has got to be for h. And the reason I know the substitution has got to be for h is they ask me up here, determine the value of r such that the total surface area is a minimum. So I want to keep the r's. I want to substitute h. So that means I first need to go and write this equation in terms of h. So I'm first going to go and I'm going to say it's 1,000 minus 4 over 3 pi radius cubed, there we go, is then equal to pi radius squared h. And then I'm going to divide on this side. Let's just do that in a different color. I'm going to divide by pi radius squared, and what I do on this side, I can also do on this side. So that means I can then eventually go and say that the height is supposed to be 1,000. And by the way, I'm just going to do distributive law here. You'll see it actually helps when I do the substitution. It's going to be 1,000 over pi radius squared minus 4 over 3 pi radius cubed divided by pi radius squared. And like I said, this helps quite nicely because I can then again go and I can say, oh, I can simplify. Obviously, this I can't simplify right now. I'm going to leave it like it is. So it's that 1,000 pi radius squared minus, and then 4 over 3 I can just write down over here. And then I can go and say pi divides into pi, and r cubed divided by r squared is then just r. So this is now the information that I'm going to substitute in here. So right there where I've got h, I'm going to substitute that in. And this, by the way, in my steps, so I've done step 1, I've set up an equation, which is over here. I've done step 2, used the additional information to set up that second equation. So now I'm step 3, substitute the second equation into that optimization equation to get that one independent variable. So area is then going to be equal to 4 pi radius squared, there we go, plus 2 pi radius times the height, and all of that is the height. So this is getting really, really messy, I know. I apologize profusely, but this was all the space they gave. You'll see this was all of the space that they gave, so I'm going to try and stick all of this in here. So 1,000 pi radius squared minus 4 over 3 radius. There we go. Now, before I can get the derivative, which is then my step 4, differentiate the optimization equation and set it equal to 0. Before I can do that, I first need to work out this product, because remember, we cannot differentiate if we have a product, so we first have to simplify. So the area is going to be equal to 4 pi radius squared And then I'm going to use my distributive law, and I'm going to say if I multiply there, 2 times 1,000 is 2,000. Then obviously pi here, because it's over 1, pi will divide into pi. And then careful, r will go into r squared r times, but this will remain in the denominator. I don't want that in the denominator. I want to bring it up to help me with my differentiation. Then I have to multiply that 2 pi r with minus 4 over 3r. So if I multiply over there, I can go and I can say 2 times 4 over 3 is going to be equal to 8 over 3. Pi needs to be written over here, and then obviously r times r is going to be radius squared. So let me just put a line down the middle so you don't get confused. So finally, I've got that optimization equation in a format that I can use it. So now I can go and I can say, let's differentiate that optimization equation and set it equal to 0. So the derivative of a is then going to be equal to, and please remember pi is a constant. So 2 times 4 pi is 8 pi radius. And then minus 1 times 2,000 is minus 2,000. Careful, r to the power of negative 2, because I have to make that exponent 1 less. Minus, then 8 over 3 times 2 is going to be 16 over 3. And then I've got pi radius. Right, so that's pretty much what I've got. Now, you might notice, and I could have actually done it in the previous step, that these two terms are like terms. So I could actually have added these two terms before I found the derivative. If you did that, that's 100% fine. I'm now going to add those two terms just to make it easier to solve the equation. But in the meantime, I can take that derivative and I can set it equal to 0, which is how I find maximum and minimum. So as I said, I'm just going to go and say 8 of those minus 16 over 3 of those. So 16 over 3 of those pi radius is going to be 8 over 3. So that means I can collect those two saying it's 8 over 3 pi radius minus, and I can fix this one up, changing that negative exponent to a positive. That's mostly why you change the negative exponents into positive, because it helps you to solve the equations. So now I've got an equation with fractions, and the fractions, the lowest common multiple of the denominator is going to be 3r squared. So I'm going to multiply by 3r squared. There we go. So that's 0 is equal to, now there 3 divides away, but I still need to multiply by that r squared. So that's going to give me 8 pi radius cubed minus, there I need to multiply 3 by the negative 2,000, which is negative 6,000, and then radius squared divides into radius squared. So this actually, even though it looked super complicated at the beginning, is not that difficult. I can transpose the 6,000 and say 6,000 is equal to 8 pi radius cubed. And then I can go and divide both sides by 8 pi. So again, running out of space. I don't know how they decided people would be able to do all of this in this little space. So I can divide both sides by 8 pi, which means 6,000 over 8 pi is then equal to the radius cubed. And then finally, I can work out the cube root. Okay. And please remember, with a cube root, you don't have to put plus minus, because with a cube root, if this is positive, there can only be positive in the answer. So then I go to my calculator and I say I need to work out the cube root of that 6,000 over 8 pi. And that gives me, if the radius is equal to 6,2 meters, correct to 1 decimal place, then I know I've got a maximum surface area. Or was it a minimum? Darn, I've forgotten. Minimum. It was a minimum. And because I have only one answer, if you have only one answer, that answer is the correct answer. So you don't have to worry whether that gives you a maximum or a minimum. The answer you get is what you're trying to get. In this case, the minimum surface area. So yes, this is super messy, but hopefully if you follow along in the video and you write it out not in this enclosed space, it will make a lot more sense. Okay, now we're going to do another example. The next example over here comes from the 2015 paper 1. So this is the 2015 IB paper 1, and it's question 10. It says, the diagram below shows a solid right circular cone that is set centrally within hemispherical container. Now, the biggest problem that I had with this particular question in the final exam is the drawing itself. That does not look like a hemisphere. I think that looks more like an egg. So I always tell people just redraw. Redraw until it actually looks like a hemisphere, which that is a little bit better, and even roughly that already looks better. And then we've got that cone that's set inside that hemispherical container. There we go. So this is going to be easier to use than this one when I get into all the different information. Right, so they tell me the radius of the hemisphere is 5 times square root of 3. So if you think about it, the radius is going to lie over there. And that is going to be 5 times square root of 3. But because of this horrible diagram over there, a lot of people didn't realize the radius in a hemisphere always goes from the center to anywhere on the circumference. So it doesn't matter where I go, this will be the radius, this will be the radius, and very importantly, this will be the radius. Now it's difficult to spot here because this looks shorter than that, but if you redrew it, then you'll realize these actually look like each other. Maybe not as accurately as you'd like, but this is going to be 5 square root 3, and this is also going to be 5 square root 3, because from the center anywhere to the circumference, that is going to be equal to the radius. Right. Now it says, of all possible right circular cones that can fit into the hemisphere, calculate showing all working the value of x, okay, which is the height of the cone. So we need to go and we need to put over there, we need to put x, which is the height of the cone. Now careful with that x. We can't go and say x goes all the way to the top, because as you can see, that does not touch the top of the hemisphere. So that flat base of the cone does not touch the top. So from there down is going to be the height of the cone, for which the cone will have a maximum volume. So that is what we were reading this whole thing for. I want to know the cone must have a maximum volume, because remember, we always need to spot what it is we're trying to maximize, because that's the formula we need to set up. And then they say, let the radius of the cone be equal to p. So the radius of the cone is up there, up top there, right there. That's p, it's the radius of the cone, not the radius of the hemisphere. Please don't get the two confused. Now they've given me some useful formula. They've given me the volume of a sphere formula, and they've given me the volume of a right circular cone. But if we follow our steps, the very first step says identify what is being optimized and set up an equation. So in this case, we are optimizing the cone volume, so the volume of the cone. So we need to set up an equation for the volume of the cone. So they've given me the volume of a right circular cone right there, so I can actually just copy it down and I can say the volume is equal to 1/3 pi radius squared times height. And please people remember that refers to the height of the cone. Now they told me the height of the cone is x, so I can actually substitute that height with x. There we go. So I can say the volume is then going to be 1/3 pi radius squared times x. Now, some of you guys go like, oh, but can't I substitute the radius with 5 square root 3? No, because this is the radius of the cone. 5 square root 3 is the radius of the hemisphere, so please do not get the two confused. Right, so now I've done step 1, I've identified what is being optimized, and I've set up an equation. Step 2, I now need to use the additional information to set up a second equation. Now the additional information is located right over here, and I'm just going to redraw hopefully so you can see it. Hopefully somebody is shouting or somebody is thinking, hey, look at that, Pythagoras. Definitely. There's a Pythagoras right over here. That is additional information. Where this is x, this specifically is the radius of the cone, which is p. By the way, we can actually go and we can change that r to p, because they said the radius of the cone is p. So it actually helps just to substitute that in there. So this is p. And then we know that the radius of the hemisphere is 5 square root 3, which is also that side length or slant height. So the radius of my hemisphere is going to be the slant height of my cone. So I can put that 5 square root 3 in there. And I can write that down. So in terms of Pythagoras, I can then go and say that p squared plus x squared is then equal to 5 times square root 3 squared. There we go. Now, please note that I'm not going to go and work out p. Why do I not want to work out p? Because my next step is a substitution. And we can actually just work out p squared and substitute p squared in there. So right there, we can just substitute p squared into that entire one. So I can then go and say p squared is equal to, now this is going to be 25 times 3. So 25 times 3 is 75 minus x squared. And then I can go for my next step, which is substitute the second equation into that optimization equation. So I can then substitute p squared with 75 minus x squared. So it's going to be a third pi times 75 minus x squared times x. There we go. And again, I know the next step is going to be I need to go and find the derivative. But people, you cannot find the derivative of a product. You will first have to go and simplify this. So in order to simplify, I'm just going to collect that third pi x in the front, because it actually will make the whole thing a little bit easier. And then I'm going to do a distribution. Please remember, I am allowed to move that x to the front because the order in which you multiply doesn't matter. So I've effectively multiplied those two, gotten this, and now I will go and I will distribute into the bracket. So if I multiply a third by 75, then a third times 75 is 25 pi x. And then I multiply a third pi x by x squared, which gives me minus a third pi x cubed. There we go. Right. Then going back to the steps, I have now substituted. So the next one is differentiate the optimization equation and set it equal to 0. So find the derivative, which is going to be 1 times 25 pi, which is then just 25 pi. And remember, x goes away. Minus 3 times a third is 1. So 1 pi x to the power of 2. I will set that equal to 0 because remember, optimization always make the first derivative equal to 0. So 0 is 25 pi minus pi x squared. And then again, I can transpose and say pi x squared is equal to 25 pi. Divide both sides by pi, which gives me x squared equal to 25. And then I'm going to use the square root, but I remember people, plus or minus. I know we're probably not going to use the minus over here, but it's just a good habit. Whenever you use that square root, put the plus minus down. So x is equal to plus or minus 5. But logically speaking, we can't have a length that is negative. So I'm then just going to go and say x is equal to 5. Now the question said, over here, of all possible right circular cones that can fit into the hemisphere, calculate showing all working the value of x for which I have a maximum volume. So I'm done. I'm actually done because I've worked out if x is equal to 5, I've got a maximum volume. I am quickly just going to do a follow-up. What if they didn't just ask me for which value of x do I have a maximum? What if they asked me what is the maximum volume? Then people, you would have to go back and you'd have to go and substitute this 5 into here, because that's the formula that actually gives you the maximum volume. So if you want to go and you want to substitute in just to check what the maximum volume is, you're more than welcome to do so. But we have answered the question, so we are pretty much done. Now with a little bit of extra time, I want to do a Michelle method. And Michelle method, like I said, is a checklist. So here's my checklist. My checklist is, what have I learned up to now? So what should I be able to do? So what I should be able to do in the first place is I need to be able to do first principles differentiation. That was right at the beginning. You need to be able to calculate the first derivative by using first principles. So you might want to go and just check that. Then you need to also be able to use the differentiation rules or laws. So you need to be able to use those to find first derivatives, second derivatives, and so forth. Then you need to be able to calculate the tangent to a curve. Then you also need to know what is the meaning of the second derivative and the first derivative. So you need to know, I'm just going to write it as the meaning of the derivatives. So the meaning of the first derivative, which talks about gradients, so that increasing and decreasing, and then the second derivative, which talks about concavity, concave up and concave down. You need to understand this. Then you need to be able to draw a cubic function. So draw the graph of a cubic function. And when you draw the graph of that cubic function, misspelling. Okay, so when you draw the graph of that cubic function, obviously you need to be able to do all the calculations involved with it, which is calculate the x-intercepts, calculate the y-intercept, calculate the stationary points or turning points, and calculate the point of inflection. You also need to be able to answer questions like where's the graph increasing and decreasing, referring to the first derivative, and also where's the graph concave up and concave down, referring to the second derivative. Then you also need to be able to calculate the equation of the graph of a cubic function. So how to get the equation of the graph of that cubic function. And you saw in the examples that we did that they have those lovely follow-up questions where, again, after you've gotten the equation of the graph of the cubic function, they can then ask you, again, calculate the missing turning points. Again, where's the graph increasing and decreasing? Again, where's it concave up, concave down? Where's the point of inflection? That type of stuff. So you also need to be able to do those graph interpretation questions. Then after that, we went and we looked at the graph of the derivative. So that one, pretty tricky, but just maybe go and watch the video again. Like I said, sometimes you need to watch it a couple of times in order for it to sink in. And then the stuff that we've done today and in the previous video, which is maximum and minimum or optimization. Now there's only really two sections left, and those two sections, I'll just show it to you so that when we continue, you can just remember those two sections. The first one is rates of change. We'll get to that later. And then the second part that we also haven't covered is calculus of motion. And then we are pretty much done with this chapter. Please don't stress, we will do more past paper examples. There will be ASP set up. But as you can see, we've actually done quite a bit. So thank you for listening, and hopefully thank you for partaking in this whole online experience. And yeah, I hope it's been a pleasant experience for you guys. It's definitely been a steep learning curve for me. So when you get back, you can give me some pointers on maybe how to do this better in future. Cheers.